Okay, I want to take some time to introduce the idea of implicit differentiation for you here, so that we can kind of keep the pace with class, since we had missed class today due to weather. There are two ways to talk about equations, specifically right now just talking about functions. And as we talk about functions, we can talk about them either implicitly or explicitly, as we've been doing. That would be writing an equation like y equals 1 over x, or y equals 2x plus 5, where the equation is explicitly stated as one thing in terms of the other, specifically y in terms of x. Or we could talk about our equations implicitly. So instead of saying y equals 1 over x, we could say xy equals 1. Or we could say 2x minus y equals 5. Now in both of these examples, we're able to figure out, solve each of those equations for y, but you could very easily have equations like x squared plus xy plus y squared equals 4, where it's very difficult, if not even possibly impossible, to write that as a closed expression, y in terms of x. And so we want to look at implicit differentiation as a means to differentiate these equations that are not explicitly defined. They're rather implicitly defined. The key ideas behind implicit differentiation there's two of them really. The first one is that we treat the other variables as functions of x, even if they may not be actual functions of x. They may end up being some relation. We still treat it that way. And so, when we take the derivative of some other variable, we realize, because it depends on x, that we have to have a dy dx. So derivative of x with respect to y would be dy dx. If instead we had derivative of y squared, we would say, well, we would do the derivative of that with respect to y, the outer function variable, and then treating y as being dependent upon x, we would differentiate y, so that the whole derivative would become 2y, and then because we were differentiating y with respect to x, we have a dy dx term. The difference between this and writing, say, the derivative with respect to y of y squared is just 2y, is the fact right here that in this second example, those two little things both agree, whereas here they do not. And so we assume that y is in some way dependent upon x, even though we're not really sure what that way is yet. Okay, so that's the first assumption we're going to use when we work with implicit differentiation. The second big thing is that differentiation turns out to preserve equality. In other words, if we have some expression involving x and y on one side, some other expression involving x and y on the other side, then if we differentiate both sides with respect to x, we're confident in saying, using the implicit differentiation rule that we've just developed, that this is also true. These two ideas are key for us to now differentiate functions using implicit differentiation. And in the following examples, we will see how to actually use implicit differentiation. So stay tuned for the next video.